In this video, I'm going to explain how to do calculations needed to solve buffer problems. Buffer problems are mainly one of two types. First, I'll explain how to calculate the pH of a given buffer, and then I'll explain how to prepare a buffer at a particular pH. This involves calculating the ratio of conjugate base to conjugate acid that's needed. As I explained in my previous video on how buffers work, buffers consist of a mixture of a weak acid and its conjugate base. On these slides, HA represents the weak acid and A- represents its conjugate weak base. First, let's discuss the equations we'll use. We're starting with the equation for the dissociation of our weak acid, HA. Notice that when HA dissociates, it breaks up and it forms A-. The equation for the equilibrium constant for this dissociation, Ka, is H plus times A- over HA. Dividing both sides of that equation, the Ka equation, by H plus gives us what I'm going to call a handy equation because it will be handy for some of our calculations. Note that this ratio, this equation shows that the ratio of Ka for the weak acid to the H plus concentration is equal to the ratio of the conjugate of the A- to HA, or in other words, the ratio of the conjugate base to weak acid in our buffer. The Henderson-Hasselbalch equation is easily derived from the handy equation by taking the log of both sides and doing a little subtraction. We'll use both of those equations here. There's also a little calculation shortcut that we're going to use in these equations. Remember, brackets means concentration in moles per liter, and our HA and A- concentrations are in units of moles per liter. And in our buffer, the A- and HA are combined. They're in the same container, and thus the value for liters, L, in the denominator is the same for both the weak acid and the weak base. That means we can use the ratio of the moles in place of using the ratio of the concentrations. That will be useful because it means we don't have to worry about the final volume of the solution. Okay, so calculating the pH of a given buffer. In these types of problems, you're given the concentrations of the weak acid and the conjugate base and are asked to calculate the resulting pH. And so here is a sample problem. You calculate the pH of a buffer containing 0.100 molar acetic acid and 0.150 molar sodium acetate. And I'm giving you the Ka of acetic acid is 1.76 times 10 to the minus fifth, and the pKa, or opposite of the log of the Ka, is 4.75. First, we'll solve this problem using the Henderson-Hasselbalch equation. So you can see here's the Henderson-Hasselbalch equation. We've substituted the pKa is 4.75, and we have the log of our ratio. And then when you calculate the log of 0.150 over 0.1, you get 0.18. So our pH is 4.93. Let's also use the handy equation for calculating this pH. Here's our handy equation. And then when we make our substitution, we'll put in the Ka over the H plus concentration is 0.15 over 0.1. We have to do a little algebra, cross multiplying, to solve for H plus. It's 1.76 times 10 to the minus fifth divided by 1.5. Therefore, our H plus concentration, which is 1.17 times 10 to the minus fifth, when you take the negative log of that, you get a pH of 4.93. So it's true that using both methods gives us the same answer. That's a good thing. And it's also always a good idea to check that your answer makes sense. It's so easy to mix up your conjugate base and acid and substitute the wrong one. So let's just make sure that our answer makes sense. Since our mixture contains a little bit more weak base than weak acid, and notice our pH 4.93 is a little bit more basic than our pKa of 4.75. So that means our answer does make sense. Now let's consider how to make a buffer at a particular pH. Since a buffer is a mixture of weak acid and its conjugate weak base, there are potentially three different ways we can make such a mixture. First of all, we could just mix solutions of HA and A minus, or we could just start with a solution of weak acid and then add strong base hydroxide to convert some of the weak acid to weak base. Notice in the equation, when you add strong base to weak acid, you convert it to weak base and water. So starting with weak acid, if we only add, if the amount of strong base is less than the amount of weak acid we started with, we end up with a mixture. Similarly, we can start with a solution of weak base and add strong acid to convert some of the weak base to weak acid. In the equation, strong acid plus weak base gives you weak acid. Another way to think about these equations is if in the battle between the strong acid and the weak base, the acid wins but gets weakened. So you end up with weak acid. And so as long as the amount of strong acid we're adding is less than the amount of weak base we started with, we end up with a mixture. So let's calculate how to make these buffers. A sample problem might be to calculate how to use acetic acid and sodium acetate to make a buffer with a pH of 5. Again, the Ka of acetic acid is 1.76 times 10 to the minus fifth, and the pKa of acetic acid is 4.75. So the way we're going to approach this problem is what you need to do is calculate the A minus HA ratio, and we're going to use the handy equation to calculate the ratio that we need. And this calculation is much more easily done using handy equation than Henderson-Hasselbalch. So notice that our A minus over HA ratio is simply the Ka over the H plus concentration. In this case, our Ka is 1.76 times 10 to the minus fifth. And since the pH we're aiming for is 5, that means the H plus concentration is 1 times 10 to the minus fifth. And we can plug that into our equation. So the A minus HA ratio we're aiming for is 1.76 to 1. So the idea is we're going to make a mixture where the ratio of sodium acetate to acetic acid is 1.76 to 1. Okay, now that we've calculated our ratio, we're ready to talk about how to actually make this buffer. In this case, we want to make a buffer where the ratio of sodium acetate to acetic acid is 1.76 to 1. And remember, that's the ratio both of the concentrations, but also just the mole ratio, and we don't have to worry about the volume of the solution. And as we discussed before, there are 3 possible ways of making such a mixture. The first would be to make a mixture of solutions of the weak acid and the weak base. So for example, we could mix 176 milliliters of 1 molar sodium acetate with 100 milliliters of 1 molar acetic acid. In this case, we'd be mixing 0.176 moles of acetate with 0.1 moles of acetic acid, and thus coming up with the 1.76 to 1 ratio. In my example, I arbitrarily picked 1 molar. Really, you could use any 2 solutions where the concentration was the same. And we talked about starting with weak acid and adding strong base. So we could make such a mixture by, for example, mixing 276 milliliters of 1 molar acetic acid with 176 milliliters of 1 molar sodium hydroxide. In this case, we've started out with 0.276 moles of acetic acid, and we've added 0.176 moles of strong base. And so what we end up with is 0.1 mole of acetic acid remains, and we formed 1.76 moles of sodium acetate. So notice we end up with a mixture. And the ratio again is 1.76 to 1. And as mentioned before, a third way to make such a mixture would be to start with the weak base. So for example, we could mix 276 milliliters of 1 molar sodium acetate with 100 milliliters of 1 molar HCl, strong acid. In this case, we'll be mixing 0.276 moles of sodium acetate with 0.1 moles of H+, ending up with 0.176 moles of sodium acetate remaining, and we've formed 0.1 mole of acetic acid, again, ending up with a 1.76 to 1 ratio. In summary, we've seen that you can calculate the pH of a buffer given the concentrations of weak acid HA and weak base using either the Henderson-Hasselbalch equation or the handy equation. And to make a buffer at a given pH, first calculate the ratio of moles of weak base to moles of weak acid needed. And we talked about 3 ways that you could make such a solution once you know that ratio. This video and the earlier one on how buffers work are posted on my website, chemistrysky.com. Thanks for listening.